In this discussion, we are going to focus on solutions. So we're going to look at what a solution is as well as how we calculate the concentration of solutions. So to start, we're going to talk about what a solution is. So a solution is a homogeneous mixture that contains two or more substances. So remember that a homogeneous mixture is something that looks the same throughout. Now a solution can be a solid, can be a liquid, can be a gas. So you could have a homogeneous mixture of solids, of liquids, of gases, or you could dissolve a solid into a liquid to create a solution. Now with a solution we have two main parts. We have a solute. So the solute is what gets dissolved. That's usually in the lesser amount. And the solvent is what does the dissolving. So water is the universal solvent. So water can dissolve many different substances, and that's typically what's in the greater amount. So if we think, for example, Kool-Aid. Kool-Aid is a solution. It has a solute and a solvent. So the Kool-Aid powder is the solute and the water is the solvent. So whenever you have a solution, you always have a solute and a solvent, and you need to be able to distinguish between the two. So what we're going to do is we're going to look at what happens when we dissolve copper 2 chloride in water.
So as an example, if I were to add some copper 2 chloride into the beaker of distilled water, I've just created a solution. So in this solution, we have a solute and we have a solvent. So the solute is what gets dissolved. The solvent is what does the dissolving. So in this solution, the solute is the copper 2 chloride. The solvent is water. Remember that water is the universal solvent, and so typically when we're dissolving something, we will use water as the solvent. That's what does the dissolving.
So when we put the copper 2 chloride in water, we were dissolving that copper 2 chloride. It goes through a process called solvation or dissociation. So that's when you have a soluble compound breaking down into its ions. So with copper 2 chloride, you have CuCl2 solid breaking down into Cu2 plus and 2Cl minus. So when you're looking at dissociation or solvation, you are just breaking a solid that dissolves, a soluble compound, up into its ions. So what we're going to do is we're going to look at a video that actually shows the solvation process. So we're going to look what happens when we put an ionic solid into water, what that water does.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
So when we put the ionic solid into water, the polar water molecules are attracted to both the positive cation and the negative anion. Now what these are called is ion dipole forces. This is another type of intermolecular force. So the partially negative side of water, it's partially negative because that's where the lone pairs are. The partially negative side of water is attracted to the positive cation. The partially positive side, which are the hydrogens, are attracted to the negative anion. And what happens with ion dipole forces is that it pulls the ions out of the crystal lattice, which is what an ionic solid is made of, and this creates ions that are called hydrated. They're dissolved in water. So we can describe the amount of stuff in a solution two ways. We can think about it qualitatively, which is like a description, or we can think about it quantitatively, which looks at calculations. So qualitatively, we can think of a solution as concentrated or dilute. Concentrated means it has a lot of solute in it. Dilute means it doesn't have very much solute. It has a lot of water. You can think about it as watered down. Now, quantitatively, we're looking at calculations. We're going to be looking at three different calculations. We're going to be looking at molarity, percent by mass, or parts per million, or parts per billion. So on this slide, we're going to be looking at the different ways that we're going to calculate concentration. So those quantitative ways that we look at concentration, we're going to look at that on this slide. So in this table, what you have is you have the three different ways that we calculate concentration, the formula, and why it's used. So we're going to start with molarity. So molarity is the most common concentration unit in the laboratory because it relates the amount of solute to the overall amount of solution. So when we say we're calculating the concentration of something, that actually means that we're calculating the molarity. So molarity is represented by a capital M. So the way that you calculate molarity is moles of solute, so moles of what you're dissolving, divided by liters of the entire solution. So that means that you have to take into account the entire solution. So it's moles of solute divided by liters of solution. So the next concentration unit that we're going to look at is percent by mass, or you can also look at percent by volume. So percent by mass typically expresses the mass of solution per 100 grams of solution. So for example, when you buy hydrogen peroxide at the store, you buy a 3% solution of hydrogen peroxide. So a 3% solution means that you would have 3 grams of hydrogen peroxide in 100 grams of solution. So to calculate percent by mass, you take the mass of the solute, so the mass of what you're dissolving, divided by the total mass of the solution. So again, the solution is the solute plus the solvent. So you have to take into account the total mass of solution, and because it's a percent, you have to multiply by 100. And then the last way that we can calculate concentration is parts per million or parts per billion. So the difference between parts per million and parts per billion is just what you multiply by at the end. So parts per million and parts per billion are used when concentrations are extremely low. So it's typically used to talk about trace amounts of something. So usually that's contaminants. So if you're looking at contamination in the water supply or poisons in the bloodstream, you're looking at parts per million or parts per billion. And so the way that you do that, it's just like percent by mass. It's mass of solute over mass of solution, but instead of multiplying by 100, it's parts per million. You're multiplying by 1,000,000, 1 times 10 to the 6th. Now, if it's parts per billion, right, instead of an M, this is a B, that means you would multiply by 1 times 10 to the 9. So if it's parts per million, it's 1 times 10 to the 6th at the end. If it's parts per billion, it's 1 times 10 to the 9. So percent by mass and percent by volume and parts per million, parts per billion are essentially the same thing, right? Mass of solute, mass of solution. Or if it's volume of solute divided by total volume of solution. Now, one big thing down here is the role of density. So the role of the entire solution's density. So the entire solution. So the role of that, so remember density is mass over volume. So density allows us to convert between mass and volume. So this is going to be really helpful as you're working through calculations. If you're given the mass of a solution, but you want to calculate molarity, you need to know the volume of solution. Density lets you do that. Density lets you actually convert between mass and volume. So what happens when we dilute a solution? So a solution is diluted when you add water. So if a solution is dilute, that means you have a small amount of solute in your entire solution. So a diluted solution is when you have way more solvent than solute. Right? Typically, we think about it as being watered down. Now, this might be one of the most important calculations in the solutions unit. When you are calculating concentration during a dilution, you're going to use M1V1 equals M2V2. So notice it's a capital M1, capital V1. So what that is molarity and volume of the first scenario equals molarity and volume of the second scenario. Now a dilution is the same substance. So you're taking a concentrated substance and you're diluting it down. So you're going to take the molarity and the volume of the initial equals molarity and volume of what you're trying to go to, and then you're solving for one of those variables. So you'll end up dividing something over. So what we're going to do next is we're going to actually look at some example problems that are looking at molarity and percent by volume and looking at using density and dilutions. So we're going to go through these example problems, so make sure that you have a calculator. If you want to try to go through the example problems and then just come back and check your answers, you can definitely do that as well.
Okay, so now we're going to work through the 5 example problems that relate to solution concentration. So the biggest thing with these example problems is to focus on what you are given and then to also look at what you're trying to find. So with each of these example problems, make sure you go through and you're writing out the equations, because when you write out the equations, that's going to help you see what you might already have and what you're trying to find. So question 1 says, what mass, so mass is grams, of NaCl is needed to make 500 milliliters, that's a volume, of 0.1 molar saltwater solution? So in this problem, I'm given molarity, I'm given volume, and it's asking me to find mass. So I know that I have molarity, so I'm going to write my equation for molarity. So molarity equals moles over liters. So what that means is if I'm given molarity, I can also either find moles or find liters depending on what I'm given. So I'm going to go ahead and plug in what I know. So for molarity, I have 0.1 molar. Now moles I don't have in this problem, so I'm going to write X moles. Now, liters is on the bottom. Now keep in mind, in order to put any number on the bottom, any volume, it has to be in liters. So 500 milliliters, if we make a note out here to the side, 500 milliliters is the same as 0.500 liters, because there are 1,000 milliliters in 1 liter. So you need to make sure that you know this conversion for volume. There's 1,000 milliliters in 1 liter. So that means that we have 0.500 liters. So now to solve this, you're going to multiply both sides by 0.5. And that's going to give me, if you put that in your calculator, X is going to be 0.05 moles of NaCl. Now make sure that you're going through and you're plugging this in your calculator to make sure that you're getting the same answers as me. So 0.05 moles of NaCl. Now the problem doesn't want moles, it wants grams, because if we were creating this solution in lab, we'd have to use an electronic balance, and that only measures in grams. So now we have to think back to how we went from moles to grams. So think back to when we did stoic. For every 1 mole of a substance, there's a certain number of grams, that's the molar mass. So if you add up the molar mass from the periodic table, Na plus Cl, that's going to give you 58.44 grams. So you're going to do 0.05 times 58.44, and I got 2.92 grams of NaCl. So we'll just round to 3 sig figs. So we have 2.92 grams of NaCl. So if we wanted to make this solution, we would dissolve 2.92 grams of NaCl in enough water to make 500 milliliters of solution. We're not going to add it to 500 milliliters of water. We're going to add it to enough water to make 500 milliliters total. So that's the first question. So the second question says, what is the molarity? So I'm solving for molarity. So I'm going to write over here. We know molarity is moles of solute over liters of solution. So you're going to notice a lot of times we'll abbreviate solution SOLN. And so it says, what's the molarity prepared by dissolving 5.5 grams of HCl? So we're dissolving the HCl, that's my solute, in 200 grams of C2H6O. So that's my solvent. Then it says the density of the solution is 0.79 grams per milliliter. So I know I need moles of solute on the top. So the first thing that I'm going to do is I'm going to take my solute and I'm going to convert to moles. So 5.5 grams of HCl, I'm going to go to moles. So to go between grams and moles, we use the molar mass. So now we're going to use the molar mass of HCl. So we're going to do H plus Cl, you get 36.458 grams for every 1 mole. So if I do 5.5 divided by 36.458, I get 0.15086 moles of HCl. Now, do not round until you are completely done. Right? Don't round until you are completely done. So I rounded here to 5 sig figs. You can also just keep it in your calculator. So what I'm going to do over here is I'm going to do 0.15086 moles of HCl, moles of solute. Now I need to figure out my liters of solution. So I know that I have 5.5 grams of solute. I have 200 grams of solvent. So think about what that would make our total mass of solution. So it'd make it 200 plus 5.5. So it would make it 205.5 grams of solution. Now, I don't want grams of solution on the bottom. Molarity means I need liters of solution. So what I need to do is I need to find volume. Now, they give us something here that's going to be very useful. They give us density. Density lets us go between mass and volume. So I'm going to use the density. For every 0.79 grams of solution, there's 1 milliliter. Lets me cancel grams. Now I don't want milliliters on the bottom. I want to go from milliliters to liters. So for every 1 liter, there's 1,000 milliliters. So we have 205.5 divided by the quantity, 0.79 times 1,000. Be careful when you put this in your calculator. But what you get is 0.26013 liters of solution. So you do 205 divided by parentheses 0.79 times 1,000, close your parentheses. You get 0.26013 liters. So when we divide these two, do moles divided by liters, we get 0.580 molar. Again, we're just going to round to 3 sig figs. Now, your answer might be a little bit different depending on if you kept this in your calculator or not, and that's fine. That's why it's important to show your work. So the third question says calculate the molarity. So again, I know I'm calculating molarity. So I'm going to do molarity, which is represented by a capital M, is moles of solute over liters of solution. And it says that it's 10% by mass and has a density of 0.85 grams per milliliter. So remember, density lets me go between mass and volume. But then it also says it's an HCl solution that's 10% by mass. So when you have something and it reads like that, like an HCl solution, that means that this HCl is my solute. So HCl is my solute, and more than likely it's going to be in water. So what I'm going to do is I know it's 10% by mass. So I'm going to say, okay, that's 10 grams of HCl in 100 grams of solution. Remember, percent by mass is your mass of your solute divided by your total mass of solution. So 10%, typically if we think about it, percents are always out of 100, so 10% would mean 10 grams in 100 grams of solution. So what we have to do here is if I want molarity, I'm going to have to take my top number and I'm going to have to get it to moles because molarity is moles over liters. I'm going to have to take my bottom number and I'm going to have to go to liters. So what we can do is we can start by taking this top number, start with our 10 grams of HCl, and I can start by going to moles. So I can go between grams and moles using the molar mass, and we've calculated the molar mass before. We just did it up in the problem before, 36.458 grams. So 10 divided by 36.458 is 0.2743 moles of HCl. So that's the number I'm going to put on the top. That's my moles of solute, 0.2743 moles. Now I need liters of solution on the bottom. So what I'm going to do is I'm going to take my 100 grams of solution. My 100 grams of solution, and I need to get that to a volume. Now to go between mass and volume, I can use the density here. So density lets me go between grams and milliliters. So for every 0.85 grams, there's 1 milliliter of solution. But on the bottom, I don't want milliliters, I want liters. So for every 1,000 milliliters, there's 1 liter. So I'm going to do 100 divided by the quantity, 0.85 times 1,000, I get 0.1176 liters. So for all of these problems, it's really, really important that you show your work. So I'm going to put 0.1176 liters on the bottom. And then I can divide the two. Once I have moles and liters, I can divide them. So you do 0.2743 moles divided by 0.1176 liters. If you round to 3 sig figs, you get 2.33 molar. So the way that you represent molarity, the unit is a capital M, and you read it like I just read it, 2.33 molar. So for question 4, it says a solution is 14% by mass H2SO4. Okay, so 14% by mass H2SO4. That tells me that H2SO4, here's my solute. How many moles, so I'm going to be solving for moles, of H2SO4 is in 155 grams of solution. So this is really just a percent by mass problem. So 14%, so percent by mass is mass of solute. So in that case, it's H2SO4 over total mass of solution. So my total mass of solution is given to me. It's 155 grams. And it's percent, so you have to multiply by 100. Now, if it's easier for you to forget this times 100 and just put this percent as a decimal to start, that's fine. But that's why that times 100 is there. So if I get rid of that times 100, that means I'm dividing times 100. I'm dividing to the other side. It gives me 0.14, because whenever you work with percents, it should be a decimal. So 0.14 equals X grams, because I don't know my mass of solute. Now remember, this is percent by mass, so I'm solving for mass first. X grams over 155 grams. So I multiply 155 over to the other side, and I get X is 21.7 grams of H2SO4. Now the problem isn't asking me for mass, it's asking me for moles. So I need one more step. I need to go from grams to moles. Now, how do we go grams to moles? We use the molar mass. So calculate the molar mass of H2SO4. So you have 2 times the mass of H plus 1S plus 4 times the mass of O. It's 98.086 grams. So I'm going to do 21.7 divided by 98.086. We get 0.221 moles of H2SO4. 0.221 moles of H2SO4. All right, so the very last question here says, what is the molarity of a solution of KCl that is prepared by dilution? This is an extremely important word here. Look for keywords like this. Prepared by dilution of 855 milliliters of a 0.475 molar solution. So 855 milliliters of a 0.475 molar solution. That tells me that these numbers go together to a volume of 1.25 liters. So we're looking for molarity. We're given volume molarity, and we're given a second volume. Keyword is dilution. The dilution formula is M1V1 equals M2V2. So I need to match up my numbers. Now, it doesn't matter what is your 1s and what is your 2s. What matters is that you have the correct numbers matched up together, so the volume and molarities that go together, and you make sure that your units match. So when I look at this, I notice that this volume is in milliliters, this volume is in liters. It doesn't matter which volume unit you pick, but they have to be the same. I'm going to convert this milliliters to liters because I just divide by 1,000. If you want to use milliliters, that's fine. You would just convert liters. You just multiply this by 1,000. So I'm going to make this my 1. So I'm going to do 0.475 molar times 0.855 liters equals, I'm trying to solve for M2, times V2, which is 1.25 liters. Now, we divide. We need to get M2 by itself. So I'm going to divide both sides by 1.25 liters. It's going to cancel this out. Now notice my liter units cancel. I'm left with molarity, which is what I should be solving for. So I'm going to do 0.475 times 0.855 divided by 1.25, I find that my new molarity after the dilution is 0.325 molar. So don't forget units as you go through these problems. So that's it for the example problems. Rewind, rewatch any of these examples if you need to, but make sure that you've gone through and you've tried them in your calculator.